Hello, this is another video for OCR A-Level Chemistry, this time on the topic of mass spectrometry. So for OCR we do not need to know the full workings of a mass spectrometer, so I'm going to just jump right in here and say that in a mass spectrometer compounds lose an electron and then they form a positive ion. And this is really crucial. All your answers to these questions will have to refer to the fact that you're forming a positive ion. Positive ion. Always a positive ion. I hope that we've got that. Why would we want to do this? Well, this is another of our investigative procedures to identify molecules. So there are two main ways that it's used. The first of these is from something called the molecular ion. There's that ion bit again. Make sure you put a plus in, and this is signified as an M, capital M. I've put it in square brackets here. I'll show you why later on. The molecular ion is used to determine the molecular mass. So if you've got an unknown compound, if you take a mass spec of it, you can work out what the molecular mass is, and that can go some way towards helping you to identify what the compound is. So I'm going to start off with a compound that I'm telling you we know what it is, to try and show you how this would come into play. So for ethanol, hopefully you could all follow by using the periodic table and work out the molecular mass of ethanol is 46. If you had an unknown sample and you ran the mass spectrum of it, what you would get is a little chart here. Here on the x-axis, this is the mass to charge ratio. For OCR, what we're told is it will always be a single positive charge. So if in effect this is just telling us the mass of the thing which is causing a peak. On the left hand side is relative intensity. I'll talk about that in a moment, but simply put, here you would get a peak at 46. Now, you may get a very tiny M+1 peak, and the reasons for that would be the presence of carbon-13, but it will be absolutely minuscule and it should not play any part in your identification of the molecular ion. So our biggest one here is 46. Don't worry, for the questions that you're given, it'll be much easier for you to determine the actual value. I'm drawing this on a bit of paper, so, you know, cut me some slack. Now, the second part from all of this is something called fragmentation. And what this means is when the molecules break down whilst they are in the mass spectrometer. So the process forms a positive ion, and this positive ion is a result of an electron being knocked out of the molecule somewhere. The electron may have been part of a bond. If a bond loses one of its electrons, then there's a chance that the bond could completely break. Now you will note when you check the spectra in the textbook out that they're not very neat things, because of course you can be losing hydrogens left, right and centre. But the main peaks tend to come from the breaking of the carbon-carbon bonds, or carbon-oxygen, or in this case oxygen-hydrogen within the molecule, because immediately below the peak at 46 we would also get a peak at 45. So here the peak of a mass to charge ratio at 46 is the molecular ion. This really large peak here is the molecular ion minus a hydrogen. Now, there is a magic number that we're always going to be looking for in these fragmentations, and that is 15. That is your magic number. 15 is loss of CH3. So any organic molecule which has a methyl group at the end, there's a chance the carbon bond to whatever part of the molecule from that methyl, the bond there could be broken. So for ethanol, if we were to knock CH3 off the other end of it, and if I draw it for you here, what can happen is that simply we knock an electron out of this bond and we break the molecule, we fragment it. And we will sometimes see a peak at 15. The example in the textbook for ethanol doesn't give you that, but what we really clearly do is we see a peak of 46 minus 15, so at 31 we see this really huge peak. And so we would write it down, 31 is M minus CH3 plus. Now it may be that you're just asked to identify what a peak comes, what fragment of a molecule a peak comes from, and that's how you would write these down. So you find the molecular ion, and the biggest thing you're looking for is a 15 below that number, and you simply can put it as the loss of methyl. It's M molecular minus CH3. Okay, so that is the start of the molecule there. There will, as I said, be lots of other little peaks, but these, you're looking at the most prominent peaks. Now, it can be used to help to identify molecules. So, what I've got here are two isomers. I've got pentan-2-ol and 3-methyl-butan-2-ol. Let's say that we had a mass spectrum and we discovered that there was a peak at 88 which came from our molecular ion. Well, that's all very well and good, but it does not allow us to identify two isomers. So what we would have to start doing is looking at the fragmentation patterns. Now, I've drawn out a few different versions so that my diagram doesn't get too messy. The very first, as I've just said, thing we're going to be looking for is 15. That's our significant thing. And what we could have is we could lose a methyl group off the end here. We could also lose one here. In this one we've got 3 methyl groups we could lose. Let's take that one. And what you would find is that both of these molecules would have a peak at 73 on the mass to charge ratio, and for both of them this is the molecular ion with the loss of a methyl group. So I haven't yet been able to determine which one I've got here, because both molecules would give a spectrum with a peak at 88, a peak at 73, possibly a peak at 15. So let's keep going. You're looking for breaking the significant bonds. I've tried to write it out in a way that really shows you where the significant bonds might be. So we could lose a CH3. Let's try breaking here, another of these carbon-carbon bonds. Another really important number for you is 43. 43 equals C3H7 plus, and you would get potentially a peak at 43, and you would also get this peak here at 45, and you could write that this is the molecular ion with the loss of this propyl group. Okay, so this is quite exciting. Could we get a peak at 43 and a peak at 45 over here? Well, unfortunately, yes. We could break that bond, and this lot adds up to 43, and this is identical. So I haven't quite got it yet. There would be peaks at 88, at 73, possibly at 15, at 45 and 43 for both molecules. We don't despair, we keep going. If we break here, well, we're still getting the 15 and 73. What about if we break the molecule here? This lot would add up to 29. And so I'm going to put square brackets around it. I didn't do it last time. The ethyl peak at 29 is another really significant peak that you need to be looking for. Your key number is 15, but you're going to closely follow it with 29 and 43. You're going to be looking for these patterns. 43 tells you that you've got a propyl, 29 tells you you've got an ethyl that's possible to be made, and 15 tells you that you've got a methyl it's possible to make. So for the pentan-2-ol, you could get a peak at 29, and then if I take 29 away from 88, then we will get a peak of 59, which is M minus C2H5. But for our 3-methyl-butan-2-ol, there is no way to get a peak at 29. I could chop off a methyl here, and that's 15, and that would leave, as before, 73. But if I try and chop this one off, then I've taken away 2 15s, which is 30. So we will get a peak this time of 58, which is M minus 2 CH3s. So you will be able to use the mass spec to be able to tell which isomer you've got. Now I suspect if you're watching this for the first time, you are possibly suggesting that I've done some form of witchcraft. This is a topic that needs practice. This is the particular one that they throw at you, spotting if you've got a straight chain propyl or if you've got this isopropyl. And it's looking for, if you've got the straight chain, then you can snap a 29 of it. If you've got this branched chain, you cannot snap the 29 off. You snap 2 15s. So, thank you very much.